idea for an in-class quiz on Tuesday that revolves around this. So rather than use Excel, I think we'll use our TIs. Same kind of idea. And it might be that some of the data lands right on negative 31 or 1. You decide whether to include it or not. 69%. Got to vote for 69%?
Oh, I got 30 out of 34.
30 out of 34, which would be,
More than
if I call it 3,
69%.
70. No, 90%. I think you got too many in there, I think.
Right?
I think
35.
you got to get
35.
26 out of 35. Nathan, you got 20, how many?
I got 24.
24, 26.
24 is what I got.
It depends on whether you put some of those in or out. I'm assuming there is a negative 31 and a 1 in there somewhere. But roughly, Jacob, you guys as well. Yeah, and we have surrounding issues, obviously, because I truncated the average and the standard deviation originally. But the ballpark is this. This guy right here, this range of values, is called 1 standard deviation. Now, I want to apologize for all statisticians everywhere. The standard deviation is this little number back here, this 16. That's what the standard deviation is. As soon as you start adding and subtracting that from an average, it becomes what's called a standard deviation, or a certain number of standard deviations. Why statisticians did that, I don't know. I wish they had called it something else, like Charlie, or smiley face, or something else, but they didn't. Or variance. Hell, I wish they had called it the variance. 1 variance, 2 variances, or something like that, but they didn't. We're stuck with it. So if you're asked for the standard deviation of a sample, you give me back S. If you're asked to take that and add and subtract it from an average, that's when it becomes, in quotes, a certain number of standard deviations. Now I want to keep going with that. Oh, there's a question. Karen,
You
go.
would say 31 and 1 are 1 standard
The range,
deviation.
yes, the range of negative 31 to 1 is the range of 1 standard deviations. Or 1 standard deviation, not plural. 1 standard deviation. So that range of values, 1 standard deviation, you could write it a couple different ways. You could write it as x bar plus or minus s. That's one way of writing it. You could write it as an interval, x bar minus s up to x bar plus s. A couple different ways. They all mean the same thing. But as Carolyn said, it's the range of values. You're given the endpoints of negative 31 and positive 1. All the values between that represent 1 standard deviation. What I was trying to do with your height data was trying to establish the range of values of 1 standard deviation for the girls, 1 for the guys, 1 for the whole class, see if there's any differences. But the problem was, your guys' heights aren't what? Oh, we'll come back to that question. That's not a good, wrong time for that question. We'll come back to it. Okay, let's come back to 1 standard deviation. Let's come back to that 69% in a moment. That is not the most common measure of a standard deviation. The most common number of standard deviations that is used in industry, in psych research, in social research is 2. Is 2 standard deviations. That's the most prominent in research. So what you would do for 2 standard deviations is go 16 more out from the ends of that one. That would be 2 standards, plus use different colors, which is green. So if you start at 1 and go out 16 more, you bump out the 17th, right? So that would be about maybe here-ish. 17 pound weight gain. If you bump 16 more down, negative 48, I think. Let's see, 10, 20, 30, 40, 50. You're not here. This one, whoa. I keep forgetting these are shorter than the other ones. This range of values, notice how it's wider than the previous? It's wider, but it's also, how is it similar to the other one? Still centered on X bar. It kind of has to be. You're starting at X bar before it, aren't you?
Still proportionate.
Good! Very nice, very nice, very nice. But we formed it by taking X bar and adding 2 of those little S guys, and then X bar and subtracting 2 of those little S guys. Now clearly we picked up more data. We picked up more data. We went twice as far out, we should probably get twice as much data, right? Careful. If we picked up 69% on the first, can we pick up 138% if we go twice as far out? No, because you're out of data at that point. Plus you're over 100%, which makes no sense. We'll come back to how much you get more. Go ahead ask that question.
Wouldn't just the first one be the most necessary and the most meaningful?
That's a loaded question, a fantastic question, but a loaded one. And I have a number of different answers for you. I have a number of different, if all you're looking for is the mode, the biggest chunk in between, then yeah, I think the answer is yes. If you're looking to minimize errors or to raise confidence in studies, the answer is no, you need at least 2.
Okay.
So, but again, you're getting into like 244 territory, which I love, thank you for that. But no, 2 is generally fair. This one right here, this guy right here, this 2 standard deviations is the most uniformly used in research. This is the one that's measured against. Because what it does is it minimizes both what are called type 1 and type 2 errors, false positives and false negatives.
Okay.
Sherry, go!
Why is it 48 instead of 47?
Down 16 from, because I can't add. A mistake, sorry. Sorry, YouTube world. Always call me on that. Because I was accounting for the rounding error. Because I screwed up. So now, Natasha, you have a question?
No.
Did you good? Scratch
Scratch
my
my
eye,
eye,
sorry. You can go as many or as few standard deviations as you want. I saw you go 5 earlier, Jake. I thought. Was that?
Physics research is 5.
Good. There's something called 6 sigma, which can also be called 6 standard deviations. For physics research, it sounds like 5 is used. I'm guessing your tolerances are really tight though. Because 5 standard deviations here gets you into like ridiculous range of, gaining 100 pounds or losing 200. But yeah, for tolerances that are very tight, 5 might be more acceptable. Good, very good.
So comparing our first to our second, and our second to our third.
Nice! Let's do that.
Okay.
Let's
I
do-
just
go,
was
go.
wondering how they.
Yes, and this is the whole point. This is the coda, if you will, of this. You can go out as many or as few as you need. For example, we already had a vote for how many were within 1 standard deviation. Well, here's if you have, and this is a big if your data is roughly bell-shaped, and I think we can argue that that looks roughly like a bell. I think we can argue that that roughly looks like a bell. It's not perfect. Guess what? It never will be perfect. If it's perfect, I think I've told you this before, that's why Harrison Ford was running away from the guy with 1 arm. The data was too good. If the data's too good, it's most likely fake. It's got to have some noise to it. It's got to have some noise to it. That's noisy, but it's not so noisy as to rule out the fact that it's bell-shaped. If it's bell-shaped roughly, number 1, trust that average. Trust the average. The average is like an ADHD child like myself. It likes rapid changes, and the average will head towards outliers. So if you've got a highly skewed data set, the average goes, ooh, blank Chinese, right? The median and the mode don't. The median go, that was a weird data point. Don't worry about that so much. Let's look at this big chunk of data over here where the normal looks like. But the average goes, ooh, ooh. With bell-shaped data, you've got these beautiful symmetric tails. So the ADHD child goes, ooh, 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 but balances back to the middle. So when you have this symmetric unimodal bell-shaped data, the average, the median, the mode, all the centers are essentially, we mentioned this before, all the centers are essentially in the middle. So you can use the average confidently, which means you can then develop the standard deviation confidently. Does that make sense? So number 1, trust the average. Number 2, you get some beautiful percentages. You get some beautiful percentages. Roughly, and now this number varies depending on how noisy your data set is. I've heard the number, I like to use the number 2/3. About 2/3 of your data is within 1, let me not do it this way, within, to save you guys the writing. I took some of that away, hopefully that was okay. About 2/3 of your data is going to be within 1 standard deviation of X bar. About 2/3. I heard 69%, that's close to 2/3. I'm doing Bruce math now. Right? 68, I think, is the one that very often hear in psych classes. 68% within 2 standard deviations. 2/3 is easy to remember, honestly. 2 out of every 3 data points should be within. Which is why I think Laura brought that up earlier. She's like, why isn't 1 good enough? 2 out of 3 are in there. I'm not saying it's not good enough for certain things. As long as 68% confidence or 66% confidence is okay for you, it's fine. We'll get anything published though. Go ahead, go
I
ahead.
did the second one and I got 94%.
And that's very close to what it should be perfectly. You should have about 95%, which is 19 out of 20. That's why I perked up when you said 5% before. Oh, Rory left. What he said, 5%, that's the opposite of 19 out of 20. 95% of the data should be within 2 standard deviations of average. That's the one that gets used in research all the time. You guys ever heard of a p-value of 5%? P is less than 5%. You may have seen this in research journals. P less than 5%, something is significant. P less than 5%. That's what 244 is based around, is that idea. It's because 95% of the data is within 2, 5% is outside of the 2. That's good. And there are some other ones that are used. 4, I'll use this one down here. You get almost all of your data, almost all of it, is going to be within 3. Now, of course, Jacob's going to say, wait a minute, why does physics use 5? Different tolerances, sometimes larger data sets, generate a higher and harder tail. It's actually not 100%, it's like 99.75%, which puts enough data in the tails, but you got to have larger data sets to find it. How much of ours is within 3?
100%.
All of it is? Yeah, there you go. All of it. It's a small data set, it should be. There shouldn't be any goofy outliers like -500 and
So
things
you
like
get more accurate the more deviation.
You collect more of the data. Actually, you get, believe it or not, you get the same accuracy and less precision the further out you go. What?
Well,
Now-
because you're stretching. farther
Exactly. You're actually, to use the buckshot example again, you're backing up from the target and giving the things farther to go. But you are collecting more of the data. Now, why would that be good? How does this tie back to our original question of how much do you lose on average on this diet?
Gives you more of the whole picture.
Now you can not only say a certain percentage, but a certain percentage did this much. 2 out of 3 people on the diet, 2 out of 3 people on the diet lost between, what was it, they lost between 17 pounds up to gaining 1 pound. And you can probably ignore the gaining 1 pound and say, lost anywhere from 0 to 17 pounds. Ignore the 1 pound if you want to. I mean, it's minuscule anyway in the interval. That's more powerful than saying 75% lost weight. That gives you a percentage which is close to 75% and also an amount which is also important. You see? That's kind of cool. It ties both things together. Here's one that you won't often hear about in statistics books. I don't know why, because it's so logical. So, roughly 100% of the data is within 3 standard deviations. Where is 50% of the data going to be? Where is the middle 50% going to be? So we went from 68 to 95 to 100, or so maybe halfway, 1.5 standard deviations. Logical, right? But it can't be, can it? It couldn't be 1.5 standard deviations. Think about what 1.5 standard deviations would be. Here's 1 standard deviation. Here's 2. So 68% are here. 95% are here. If we go to 1.5, that would have to be between 68 and 95%, wouldn't it? Wouldn't it?
Oh, yeah.
As the further out you go, the more you pick up. So 1.5 standard deviations would have to pick up more data than 1 standard deviation. So if here's 68%, where would the middle 50% have to be? Give me a direction to go with my hands. In. And it ends up being roughly half of your data is within 2/3 of a standard deviation from average. A very little, bloop, 2/3 of the way out. That gets you about half of your data. The middle half. It gets you the middle half. Why do you care about the middle half? We'll talk more about that on Tuesday. The middle half is important. It's called the interquartile range. Pediatricians' growth charts love those things, the middle 50%. I heard an oh gosh,
Yeah,
I'm sorry.
yeah, the people just, they base that off so much, you know,
Oh,
so much
oh,
off
Carolyn.
that little.
Well, we're going to talk in 120 hours. Because I like talking about pediatricians' growth charts because number 1, it's a perfect way to segue into relative position, number 1. And number 2, it affects so many people. And if it hasn't, it might affect you at some point when you bring your little chitlins in the pediatrician. So we'll hold that next time if you don't mind,
Yeah.
but that's tied directly to it. Yes, Lauren, finally answered your question. I'm sorry it took so long. Sometimes that happens. I'd rather take the time, answer it well, than just give you, here's because. Cool! You have enough now if you want to get into that exam. I want to talk more about this next week. I want to use some different data sets, learn how to deal with nuts and bolts of any kind of data set that you have. Also limitations of this, but you have enough now if you want to get into the exam. You can start that happily and get everything as you go to the exam. Cool? You guys rock? Have a good weekend.
I'm up close here. I got a good spot.